You are sitting on your couch, streaming a movie in perfect 4K resolution. The video doesn't buffer once, but hundreds of miles away, the physical server actually hosting your movie just sparked and died in a dark room. Your movie keeps playing because the system immediately routed your connection to another machine. But the engineers who built that system didn't simply plan for that hardware failure. They likely unplugged that server on purpose. Hardware is inherently fragile. Hard drives degrade, power grids fail, and construction workers occasionally slice through fiber optic cables with backhoes. Relying on a single, unbreakable machine is a fantasy. To understand how companies survive these disasters, we can look at the playbook of technology executive Sriram Gopalan. In Chapter 5 of his book, Bridge the Gap, he outlines the principles of designing for disaster. Networks will always fail eventually. Modern digital businesses stay online by treating structural collapse as an absolute certainty rather than a rare accident. The most basic defense mechanism is redundancy. A bridge supported by a single concrete pillar collapses if that pillar cracks, but a suspension bridge distributes the weight across dozens of cables. If one snaps, the others absorb the load. In software, engineers achieve this using an active-passive architecture. You buy 2 servers, but only one does any work. The second machine sits idle in the background, serving as a fully inflated spare tire in the trunk of your car, waiting for a blowout. This setup creates a rigid economic trade-off. You are paying 100% of the hardware and maintenance costs to get exactly 50% capacity. It is a pure insurance policy. But that spare tire only helps if the primary server actually dies. If a server stays awake but simply starts running incredibly slow, the passive backup never triggers. Buying extra servers only solves half the problem. Without a way to detect and isolate lag, your entire infrastructure remains vulnerable to systemic slowdowns. This diagram shows a cascade failure. This occurs when one struggling service drags down every service connected to it. A slow checkout cart forces the inventory system to wait, which forces the search function to stall, quickly freezing the entire website for every user. To contain that damage, engineers write code that acts like the electrical panel in your house. If you plug too many appliances into one outlet, a circuit breaker trips, cutting the power instantly to prevent the wires from melting. Software circuit breakers monitor connections. If the payment server returns 5 consecutive failures, the checkout system automatically severs the connection. All new traffic is blocked. Instead of an endlessly spinning loading wheel, the customer instantly sees a polite error message. To protect the user who might furiously mash the pay button during that lag, engineers rely on idempotency. Idempotency is a property where an operation produces the same result whether it is performed once or multiple times, ensuring a customer isn't charged twice for a single order. Circuit breakers isolate the damage, while idempotency protects the data. Together, they transform a potentially fatal outage into a minor, isolated inconvenience for a few users. Having backups and breakers is entirely different from knowing they will function under pressure. You don't want to find out your fire exits are locked while the building is actually burning. To solve this, Netflix developed Chaos Monkey. During business hours, this program randomly selects a live production server and turns it off. If the system heals, the team gains confidence. If it crashes, engineers discover the weakness during the day. Tech giants like Amazon and Google mandate similar exercises called game days. Engineering teams schedule controlled fire drills, where they intentionally sabotage a piece of their live architecture to hunt for single points of failure. True digital resilience requires an active, aggressive routine of controlled destruction to prove the safety nets hold weight. When executives demand 100% uptime from their engineering teams, they are asking for a mathematical and physical impossibility. This chart illustrates how the industry actually measures reliability using a metric called the nines. Promising 99% uptime allows a site to be dark for about 3.5 days a year. Pushing that to 5 nines, 99.999%, shrinks that allowable downtime to just 5 minutes every 12 months. That tiny reduction in downtime comes with a massive penalty. Moving a system from 3 nines to 4 nines typically multiplies the physical infrastructure costs by 10. A local e-commerce startup can easily absorb a few hours of downtime, so 3 nines is a logical choice. A global bank, however, will pay the massive premium required to maintain 5 nines because a few hours offline costs them millions in lost trades. Your server architecture reflects a financial calculation. Every extra 9 on the uptime chart represents a specific dollar amount an organization chooses to pay to avoid a specific risk. Translating these engineering trade-offs into the language of cost and risk turns technical hurdles into business decisions. Subscribe to keep building the bridge between code and commerce.